For today's webinar, we're very pleased to be hosting Andy Sharpe. Andy has enjoyed working in a variety of aspects in the environmental field over the last 20 plus years. These have ranged from environmental policy development in Malawi to gold mining in Newfoundland via local government community stewardship in the UK. He has worked with a range of government and NGO organizations and in the private sector. He's lived in Nova Scotia for the last 14 years and for the last 5 years has worked with East Coast Aquatics. He continues to enjoy the intellectual and physical challenges of working in the water bodies and wetlands of Nova Scotia. After the presentation, we'll be opening the floor for a question and answer session. You'll have the option of asking questions directly using your microphone, or you can type them in and we'll read them aloud. I will now turn the webinar over to Andy.
Good afternoon, everyone, and thank you for joining us for this talk. I think I like this cover photo in that it sort of reminds me of that summer will come back, all that nice green vegetation. Before we go any further, I just want to make sure that everyone's okay with the content with today. There are some things I'm not going to be talking about today. I'm not going to be talking about detailed water quality analysis or detailed statistical approaches to dealing with data. However, I am going to try and cover good practice with collecting and handling and presenting your data, some pointers on structuring a robust water quality program that will achieve results, and some suggestions for good study design for community-based monitoring. So that's sort of the context of this presentation. I'm going to be talking for about 50 to 55 minutes. And then, as Darla indicated, there'll be an opportunity for some questions at the end. Before going any further, I just wanted to acknowledge the Cura H2O program at St. Mary's University in Halifax. They approached us several months ago with this idea of pulling together some ideas on good practice for community-based monitoring, and that led to a workshop at St. Mary's, and then those ideas being further developed for this presentation. I want to set the stage here today and provide a little bit of context in terms of the subsequent material I'll be covering, laying the groundwork as it is. So there's a fairly clear number of criteria or factors that come out when good monitoring programs are looked at. These 5 points here, and I'm going to be talking about each of them in turn, tend to be seen over and over again in high-performing volunteer-based programs. So to take them each in turn, just explain a little bit more about what they mean. So the first one, having a good or well-organized program. That means having a clear purpose, why it is we're out there getting wet, collecting the data. These programs work within the context of other organizations requiring good partnerships and good relations with decision makers. Within the organization that's doing the actual monitoring, there needs to be good leadership and coordination with clear roles between what the staff do, what the board of directors do, and what the volunteers' responsibilities are. Coupled with that, good programs have a sound scientific basis, and that means there's clearly articulated questions, monitoring goals and questions, and a study design that's documented. There are clear instructions of how to go about the monitoring activity. And just on this point in particular, it's unfortunate, but the context we work in means that many groups, volunteer groups, community groups, have a fairly high turnover. For the groups that have staff who are monitoring community-based programs, they can't really pay them a going wage, and so they might have staff only on for summer or seasonal and a high turnover. And the implication is that community groups, unless there's clear documentation of how to collect the samples, there is typically 1 year to the next differing procedures used because of that staff turnover, because of the budget situation. And so part of a good scientific basis, a sound scientific basis, is clear instruction so that that next person who gets hired next April can pull out the notes from last year and collect consistent data. For following this on further, the monitoring has to match the group's capabilities. And I'm going to talk about this further in the next few slides, but groups have to realize that they have to be honest about their abilities, both internally, financially, structurally within a group, and what they're taking on for their monitoring. And finally, good quality assurance. And I'm going to be coming back to that as well. So finally, good programs, something happens with that data. The data is turned into a story. That story is reviewed, and it's something. There's some tangible action that results from all of that hard work of collecting the data. If we're relying on volunteers to give up their evenings and their weekends to go out and collect data for a group, for a watershed organization, that's time they're not spending at their livelihoods, with their families, in relaxing. Those volunteers need to see some results from their efforts. Not immediately, the next year, maybe 12 months later, 18 months later, but volunteers get turned off if they contribute their energy year after year to a group and the data just gets collected and nothing ever happens as a result of their efforts. And that's what I mean by turning information into action. There has to be some tangible result to give those people, those individuals, that validation that, okay, that they are making a difference. So where's our data going from this volunteer data that's being collected? Well, it could go to a bunch of different purposes that it could be supporting. There could be education. It could be to try and understand existing conditions in a water course, find the source of a problem, source of contamination, or it could be feeding into local decision making. And there's, of course, more uses. But having an understanding of how the data is going to be used, it has an important, some important considerations early on. We can sketch out how the data is being used on a continuum from left to right, education and awareness, through to legal regulatory uses for that data. As we move left to right across that continuum for how the data is going to be used, you can expect to put into that program increasing time and rigor, quality assurance and quality control, and money. And so you need to think about where your data is going. What is it being collected for? Where does it sit on this continuum? And do you have the necessary support, time, money, rigor in your program to support that eventual use? And each manager, each coordinator of a monitoring program has to kind of grapple with these considerations. What the data is being collected for, and is the necessary support mechanisms there to deliver. So, turning to specifics, I'm a strong believer that every monitoring program should have a clearly articulated question. And from this question, everything else is going to flow. But we need to start, each group, each individual coordinator needs to consider why we're going out to do this, why we're going out to get, again, in the rain, why we're investing this time and money. The question can be fairly simple, it can be fairly involved and detailed, but you need to have a question. A fairly simple one here. Is Paradise Lake safe for my kids to swim in? Well, that's something that, you know, volunteers could get behind. People would identify with something like that. How do we, okay, so now we've got our question, what's the next step? Well, we need to begin to break out the components of our monitoring plan, where we're going to collect our samples, what we're going to sample for, how often, for how long, and importantly, once we have our numbers back from the lab, what are we going to compare them to tell us whether there is a problem or not, whether the water is safe or not? So I'm going to be going through these components in more detail, but I think it's important to stress here that a question is critical to have is a critical first step in building a good water quality community-based monitoring program. Secondly, I think it's really important for groups to think through who is their target audience, because this will help guide you in how your data is analyzed and packaged. It's useful to think about what sort of action you want your audience to take based on the information, the water quality information you're going to provide them. For example, if you want a municipal council to enact a land use bylaw, what types and thresholds of water quality data will they require in order to make the decision that you want? So fill in the blank. You decide who your audience is and what you want them to do, and then build your program from right now in January through till starting collection in the spring and carrying on through your analysis to deliver to those individuals, to your audience, the necessary data in the appropriate form to allow them to make those changes that you want. So, our audiences, well, it could be the general public, it could be general information, it might be government staff at varying levels, school children, landowners, municipal councilors. Each of these groups is going to want their data in a different package and presented differently to have greatest effect. And so thinking now, early on in the year, who your audience is, and again, what you want them to do is important. So once we have our monitoring question, once we've thought through who our audience is, we need to get into the meat and potatoes of crafting our water quality monitoring plan. There's guidance on the internet, there's good stuff available. I'm not going to beat this to death. But it's as simple as these 6 questions. And your monitoring plan, this is winter work, really lays out the details of how and where and why you're going to be doing this work. And again, it's important for continuity year to year with staff changes, with different volunteers. It gives you something to hang on to refer to. Coming back to your audience, tailor your data and your program to the audience that you're seeking to influence and make a change. Think about what that audience is looking for. How much time will you have access to deliver your information? What level of detail will they be receptive to? So are we talking to an educated scientific audience, or are we talking to school children? Very different levels of detail required in your summary data. And that falls onto what sort of visuals or sound bites might be appropriate. Which leads us to, well, how are you planning to convey your data? And there's a whole range of mechanisms available to us to convey this data that we're collecting. They all have pros and cons, and so you need to think about, well, what your audience is and what's the best vehicle for delivering your data to your audience. For example, full-length scientific reports are great, lots of detail, but not many people read them, and there's typically a time lag between the data collection and when that report is available, typically months to years. So they're not that timely. On the other hand, Twitter is great, but you're constrained by the number of characters. You can't really provide any analysis. There's really no context for these numbers that you're going to be pushing out. And so then we have all these other mechanisms of conveying your data. So you need to think these parts through and identify, ideally early on now, what's the best mechanisms for reaching your target audience. The photograph here is a signboard used by the Clean Annapolis River Project adjacent to their volunteer water quality sample locations. It's one way to present timely information to local residents adjacent to a sample community. One way, but there are many ways, and I just put this here as an example. So that's enough of the background. I want to now turn to talking about data analysis. And I'm going to be using real water quality data to illustrate some points here. So here we have a bunch of water quality data, milligrams per liter, 6 sites, 6 samples 6 times a year. We've got 72 data points here. So if you were to show me this table, it wouldn't really mean much to me. I can't really, at a glance, interpret much from this set of data. And I think it's important to reiterate that tables aren't the best way to grab your audience, to convey to an audience quickly what the message is. So we need to come up with some tools to distill this large amount of data into some key points. Well, our default is to calculate an arithmetic mean, an average. That's okay. We can do that for our 6 sample sites. And what do we see? Well, site 4 here has the lowest average, but we should ask ourselves, is that value of 6.0 representative of all of the data for site 4, knowing that averages are susceptible to distortion by very high and very low numbers. So we look at our data here for site 4 and we see, okay, we've got 2 low values for site 4, but all of the other data, all of the other samples are above 6. So we should ask ourselves, is that 6.0 average representative of the whole data set, or it has been artificially skewed down by these low values? We could also use medians to examine our data. Nothing magical about medians. Here we have nine digits ranging from 2 to 120. The median is the middle value when they're ranked from lowest to highest. But what we see is, while we have a median of 10, our average is 20.5. Quite a big spread, and it's because of this skewing up from the last digit, the 120. And so probably the median value of 10 is more representative of the bulk of the numbers, but we've got this skewing up from with the high value. So medians are something to have in your toolkit and remember the impact of high and low values, which can skew averages. So if we compare averages and medians for our dissolved oxygen data, what we see is our average was 6.0, our median is 6.8, which is more representative of the bulk of the data for site 4. Taking this a bit further, we can look at a couple of other parameters, a couple of other metrics for examining data. Range, maximum, and minimum. So the range is the difference between our maximum and minimum values. The larger the range, the larger the variability in that data set. Maximum and minimum are also important because for some parameters we're concerned about max and mins. For example, we're concerned with DO, dissolved oxygen, because there are minimum concentrations needed for fish. Same or opposite applies to bacteria in that typically E. coli and other bacteria are reported as maximum levels that we don't want to exceed. And so min and max are important tools when teasing out our data set. So going back to our dissolved oxygen values, here are minimums and maximums and our range. And very quickly, with a range calculator, we can quickly see which sites have the greatest variability. Sites 4 and 5 have the greatest range or the greatest variability in data sets. Taking this a step further, quartiles and interquartile range give us a little bit more rigor in examining our data. So quartiles are simply taking our data and breaking it into quarters or chunks of 25% and to 50 to 75% breakouts of our data. And by definition, the 50th quartile is the median value. And carrying this further, half of your data is going to occur between the 25th and 75th quartiles. It's easier to explain this by looking at some real numbers. So here I've got some data values from Site 3 that you've seen already. And we've got values from 5.6 up to above 8. What we do if we want to get into and examine quartiles is we take these numbers and we rank them. We order them from highest, 8.3, down to 5.6, the lowest. So once we have our data ranked, we can then begin to tease out and show where our quartiles are and where our interquartile range sits. So our 50th quartile is our median, that's the middle of this data set. And this circle is really the center of that spread of data. And so that's where data is going to tend to occur half the time. And it's an important way to understand the variability and spread in data. It means we've got a lot of variability in our data set, which should be raising flags in our mind to investigate further. So quartiles, interquartile range, I'm going to come back to these again and use them in various ways. So we can summarize that same table of dissolved oxygen values and break out our quartiles and our medians. And again, we can immediately ask some questions of this data, and it's quite quick to be able to understand which sites had the greatest and the least variability looking at the interquartile range. So Site 2 had the smallest interquartile range, and Site 3 had the largest, with nearly double the spread of that interquartile range. Again, this is all information that should be coming to you to help you understand the broader context of what this data means. So I'd like to turn now to a different metric, and that's geometric mean. So we've covered averages, and we know that averages are susceptible to influences by very large and very small numbers. Medians are better. But sometimes we have data sets where we have very large spreads in our data, typically over several orders of magnitude. Geometric mean is a useful tool to summarize data sets when we have very large spreads. So this is how it's calculated, but fortunately you don't really need to know this. Excel does a nice job. It's one of the standard functions in Excel. And I would recommend you consider using geometric mean whenever your data covers several orders of magnitude. With an important caveat, any zero values in your data set need to be converted to ones, otherwise you get an error message. So, what are the implications? Well, typically, E. coli data, bacteria data, reported here as most probable numbers, they have a very large spread. In this table of data, we've got values from a minimum of 2 to a maximum up over 2,000. So more than 3 orders of magnitude spread in our data, and this is entirely normal for bacteria data. And so if we were, this presents some analysis challenges that we have to overcome to meaningfully convey what this means. So let's look at these in pairs, because I think it's a useful point to make at this point here. So we calculated the geometric mean and average for each of these sites. Also, when we look at these, some interesting conclusions come out. We've got 47 versus 114, 75, 236, and on down through this list. In every case, our geometric mean is smaller than our average by a significant degree. The implications. Let's say we were using the CCME, Canadian Council for Ministers of the Environment, standard of 200 E. coli per 100 mils of water. And you, the coordinator of your monitoring program, was asked by your board of directors, tell us which sites are exceeding the guideline. That's a very standard question. Tell us which sites we need to worry about. Well, if you had calculated averages with your bacteria data, you tell your board, well, sites 2, 3, 4, and 5 are exceeding the guideline. We need to worry, we need to warn the public, take action. On the other hand, if you'd use geometric means, you tell your board none of the sites exceed the guidelines. Two very different conclusions from this data set. And that has, and the reason we're getting these skewed values with averages is these really high numbers. So with sites 2, 3, 4, and 6, single high values are skewing that average up. And again, site 3 has the highest average, site 5 has the highest geometric mean. So again, if you were asked by your board, tell us which of these 6 sample sites is the worst. You meet a member of the general public and they want to know, or your volunteer wants to know, which of the sample sites on our river is the worst. Well, again, if you'd used average, you'd tell them site 3. If you use geometric mean, it'd be a very different site. And if you're using this data to then plan remedial action, spend money, ask municipal councils to take action, you've got a problem. Because if you're using averages, your numbers don't stand up. My point here is the method of analysis you use matters, because you'll get very different, sometimes very different conclusions depending on the type of analysis you use. Okay, so I've talked about a couple of things, means, medians, geometric means, quartiles. So how do we know which to use in which seasons? Well, fortunately, I've got 2 slides here which I think that will provide some guidance of what form of analysis to use for different parameters. And I believe this presentation is going to be archived with the Salmon Foundation website, so you'll be able to refer back to this. So, if you're doing temperature monitoring, here's some summary statistics that you should think about using. Dissolved oxygen, either as milligrams per liter or percent saturation, water clarity, etc. It's important to note here dissolved oxygen as percent saturation, because it gets already it's already corrected for temperature and salinity. Percent saturation values tend to be a bit more stable, and it might be okay to use average values. Whereas for your other parameters, I would, as a rule, steer you away from averages towards medians and the other metrics shown here. Some other common parameters that you might be sampling your data for, and again, medians come up again and again. Down at the bottom with pH, again, if you're dealing with a fairly well-buffered system with no extreme fluctuations, probably it might be okay to use averages. unlike medians for the other parameters. So a couple of factors to bear in mind when we think about how to summarize our data. With temperature and dissolved oxygen, because it's dependent on temperature, if you're sampling for more than one season, we know that temperature and DO will vary with the seasons. And so you should be breaking your data out and reporting it season by season, not trying to make a summary for a whole year's worth of data. Lean towards medians rather than averages. And you need some data. You need some points before you can do anything. Ideally, at least 5 data points before you can start to report anything meaningful with these values. So there's some summary values. I'd like to now turn to presenting your data. So here we've got a graph that might have been taken from a community group report. And if you showed me this graph, I wouldn't get much from it. It wouldn't really do much for me. And there's a couple of reasons why. The title, yeah, you lost me after the second sentence. The y-axis, well, bacteria, that's not very informative. There's a lot of bacteria around, and some are good and some aren't, and some I don't care about. No units. But the x-axis at the bottom, well, where are these sites? You, the coordinator, will probably know where these sites are, but I don't, the uninformed general public who looks at this graph. So how could we improve a graph? Well, here's a couple of thoughts. We could give it a better title. We could explain in the title what it is, what form of analysis was done to generate this table. On our y-axis, we could specify the actual parameter we sampled for and units, most probable number in this case. At the bottom, useful for context, where's upstream and where's downstream. So we have some level of continuity and context for this data. And most importantly, is a threshold of concern. You decide what that is, but I'm a strong advocate that every graphical presentation of data should have some indicator of where's the threshold of concern, what's the water quality objective, what are we aiming, what are we saying is too high, and anything more than this is concern. Because you've got to appreciate your municipal councillor, your member of the general public, they maybe last did high school or high school chemistry. They're not going to get into the nuances of your data analysis. You need to clearly tell them, and they need to be able to immediately grasp when they see your graphs, where are the sites of concern, which ones are not of concern, and how bad is it. And providing your viewer some indicator of threshold of concern is important. We could take this graph a little bit further and change it, rather than a bar chart, into box and whisker plots. So I'm an advocate of box and whisker plots. I think they do a great job at condensing a huge amount of data into an intelligible format that quickly conveys what that data is saying. So we already know what makes up a box and whisker plot. The center bar, the horizontal bar here, is the median value for each of these sites. The top is our 75th quartile. The bottom is our 25th quartile. So the tan colored box is our interquartile range. And then we have a maximum and a minimum. And so the box and whisker plot method allows you to quickly say, okay, well, site 1 is pretty similar to site 2 within reason, but 3 and 4 are different than those first two. This one, much bigger spread in the data, and this one, almost, not quite, but almost half the data is is below our threshold of concern. In this case, it's dissolved oxygen data. And so, and some of these values are very low, almost getting down to anoxic conditions. And so, at a glance, our box and whisker plot is telling the viewer a lot of information. So, the upside is that you can produce box and whisker plots with most statistical programs, software programs. The downside is it's not a standard graph within Excel. However, there's a lot, you just need to Google it. There are instructions on the internet of how to set up Excel to produce box and whisker plots. It will take you an hour or two to work through the instructions, to set it up as a template, and then you just use that worksheet over and over again and produce your box and whisker plots happily ever after. So you can still produce box and whiskers with Excel. It just takes a little bit of work at the front end. So, threshold of concern. Where do we get these numbers from? Here's some, and your go-to place to start with should be the Canadian Council for Ministers in the Environment, CCME. Look at the website. Specifically, if you're dealing with freshwater systems, water quality guidelines for the protection of freshwater aquatic life. However, these are all water quality objectives, and they provide some a benchmark for you to compare your data to a standard. Also relevant to check your local jurisdiction for local water quality objectives. Scientific literature, water quality objectives at the national and provincial level, and they can also be specific to your catchment. The key thing here, though, is to provide in your data analysis, graphical formats, etc., some point of comparison and clearly articulate why you've chosen your particular water quality objective and how you're using it. So in this table, I've got a bunch of values from CCME guidelines for DO and temperature, DO and pH, and TSS. If you're dealing with salmonids, which are particularly susceptible to warming water, you might have to look at some other literature for values for temperature. CCME doesn't do a good job, though, at providing water quality objectives for nutrients, phosphorus and nitrogen. So again, we have to look at some other literature that exists that gives us some threshold values for phosphorus and nitrogen that we shouldn't exceed, otherwise we run the risk of eutrophication. Now, technical advisory committees. I believe every single watershed group should have one. They come in various forms. They go under a variety of different names. But you should, if you don't have one now, think about having some sort of an arm's length group that can provide you, the watershed coordinator, water quality coordinator, with expert, impartial advice. Here's some suggestions of where that you might draw that committee from. But I think it's an important component to having a good program and generating good data. Before your data goes out the door, you should really have someone outside of your organization look over your analysis and conclusions, because it will save embarrassment. It will save you going red in the face when you realize the report's already gone out and there's a glaring error in it. This is speaking from experience. So I've talked about the steps in water quality monitoring. You've got your research question, you've got your sample plan, you collect your data, you analyze your data, you communicate. Well, where's your technical advisory committee come into this? They should be helping you articulate and finesse that research question to make sure it's really nailing what it is you're seeking to get to examine. They should have some input on the development of your sampling plan, certainly at the data analysis in terms of what methods you're going to be approaching your data in terms of analysis. And that final stage, again, double checking to make sure there's no glaring errors or misrepresentation in your communications, in the reports that are going out the door. I'm also an advocate for community groups to have good quality assurance, quality control programs. And again, this is winter work to think through these steps, but this is an important part of a good program. So precision, I'm going to just quickly touch on each of these points. Precision is how close are how close are repeated measurements to one another. Clustering. Accuracy, pretty self-evident, how close to the true value are your measurements. Representativeness, how well our samples are at being able to represent true environmental conditions. That one sample bottle that you collect from a river once might not fully characterize the diversity of water quality conditions in a river. Comparability is how well our data can be compared between sampling locations, periods of time, but within a project, and also comparability between volunteers. And completeness is how much actual valid data we were able to collect compared to our monitoring plan. So it's important to expect your audience to be skeptical, and quality assurance, quality control measures allow you to prove to a skeptical audience the value and the completeness and accuracy of the data that you're generating. This is a graph that's been used lots of times, showing accuracy and precision. We test precision by taking multiple identical samples at the same time and place, and we should get the same numbers back. Otherwise, we're not generating precise data. We test accuracy by sampling water using multiple methods. For example, if we're doing dissolved oxygen, we could sample water with both using a Winkler titration and a digital meter, or have multiple instruments, some way of comparing, are we getting true values? And I think you need to build your program so that you're evaluating accuracy and precision. So one part of a monitoring program is training your volunteers. And Clean Annapolis River Project, where I worked for 8 years, had every spring the volunteers we brought in and would have a refresher day, a training day with those volunteers, bringing them up to speed. And that's an important part of good quality control. And we get them to do dissolved oxygen determinations with the Winkler titration. And you generate some numbers from those volunteers when they're in a control setting using the same water. Now, from that, we'd be able to say, okay, well, are volunteers giving us comparable results? And from these numbers that you see here, it's obvious that John is doing something different. Tom, Jill, and Jeff, their numbers are fairly consistent and clustered. John, there's something going on there, and we would then recognize that John would need some sort of, probably he's doing something, he's making a mistake somewhere in the process and would need additional training. We could, this is relevant because we need to be confident that once these volunteers go out to their sample locations under different conditions, hot summer days, cold nights, rain, etc., that we're generating consistent results. We can collect replicates to evaluate precision in that volunteer data. Again, collecting multiple, once they're actually out collecting their data, we can do multiple splits of water samples, multiple analyses, and then begin to tease out, well, what's the typical variation that we would expect, and set some thresholds. Once you've done this a couple of times, you begin to understand where the variability in your data, in your volunteer data, lies, and where are the outliers. So where's your envelope of data that you're willing to accept, variability that you're willing to accept, and then when something falls outside that, you'll know you need to take some remedial action. Split data. So splitting samples is a useful way both of testing accuracy. In this case, volunteers analyze a sample, and a staff member analyzes a split of that same sample, and then you compare the results. And quickly you can then, by comparing differences, quickly see when you've got outliers, and so quickly identify which volunteers might need additional training on the analysis techniques. Representativeness. If you were going to say, or if I was going to say to you, I'm going to collect a sample at that location for these parameters once per year, I have to question, is that one sample really representative of environmental conditions in a lake, in this particular lake? And I throw this out because it's easy to slip down this slope of saying one sample or 3 samples is representative of the conditions in this watershed. And so you have to be reasonable in what you're claiming your samples represent. Completeness. If our monitoring plan said that we're going to do some DO and pH and conductivity and turbidity shortly after large precipitation events between April and October, and unfortunately, because of a variety of reasons, we only got out there for 4 out of the 9 precipitation events, can we really say at the end of the season that we have a complete data set? Can we really then use that data set to draw any large conclusions if we really, at the outset, felt we needed 9 sets of data? So completeness is another factor to consider when looking through your data. So to wrap this up, start with a question. Think about your audience early and go back to your audience. Who is the audience repeatedly, and plan to direct your message to that audience. Have a written plan. Have a technical advisory committee. Remember quality assurance, quality control. And I'm just going to throw in an example from my own personal experience of giving a presentation of water quality data to a municipal council. And halfway through the presentation, a fairly gruff councillor muttered under his breath that, oh, well, this data is just being collected by volunteers. It's inaccurate anyway, so why are we wasting our time listening to this presentation? I was lucky at that time that I had a good mentor, and that mentor leaned on me heavily to have quality assurance, quality control measures in place. And so in that particular presentation to that council, I had a slide documenting what QA/QC measures had been put in place and some of the splits and replicates and precision comparisons showing that the volunteer data was entirely consistent with staff collected data. But you expect a skeptical audience, address it by having good quality assurance, quality control. A couple of more thoughts. Think about your data telling a story. Think about using multiple formats and approaches to get your message across to different types of learners. And think about using good images to try and convey some of the complicated information that you're going to be generating. And with that, I will conclude and happy to hear any questions that you might have.
Thank you so much, Andy. That was a terrific presentation with a really great overview of water quality and the analysis. A lot of good food for thought there. So as Andy said, we'll open up the floor now to question and answers. To ask a question, you can use your webinar control panel, which is the little gray box that you should be seeing in the upper right-hand corner of your screen. If the box is minimized, just hit the orange arrow and that will enlarge it. If you're using the audio of your computer, you can figuratively raise your hand, which is the yellow icon with the green arrow, and we'll unmute you so you can ask your question directly to Andy. Or alternatively, you can type in your question on the control panel and we will read it aloud for you now. So we'll just give everyone a few minutes to either raise their hand or type in a question. Oh, I see a comment here from Rick Simpson. Perhaps helpful and complementary to your work with volunteers on water quality, there's the Pacific Stream Keepers Handbook, Module number 3, Water Quality Survey.
Okay.
Okay, I see Loretta Ross does have her hand up. Loretta, I'm going to unmute your microphone. Do you have a question for Andy, Loretta? Hello, Loretta. Okay, your microphone perhaps doesn't seem to be working, so if you'd like to type in your question instead, that would be great. So maybe while we're just waiting for folks to type in questions, I have a quick one for you, Andy.
Sure.
Do you have any recommendations in terms of groups that, you did mention about turnover and how that's a challenge for a lot of watershed
Yes.
organizations. I know some groups encounter a situation where they come across older data that they would like to be able to incorporate into their analysis. Do you have any thoughts or recommendations on how that can be best used?
Hope that good metadata was captured at this and recorded in the spreadsheets. It's a challenge, and I've been in that position of having spreadsheets of data, sometimes with units, sometimes without, sometimes with sample locations, sometimes without. And it's wonderful to be able to have that a longer time series, but unless there's good accompanying supporting material to the actual numbers, it's difficult to incorporate it. I don't have any quick solutions other than try and be diligent in recording data going forward to I think it's a good practice. You've got your worksheets with your actual numbers, and the first worksheet in any Excel file is the metadata, the who collected it and what they collected it with and where they collected it and why they collected it, so that that spreadsheet in 5 years' time will be useful to someone else going down the road.
That is excellent advice, and it's not something that I think folks who are collecting data always think about, but that is really good advice. So
you put all this.
Oh, please go ahead.
Well, we put all this energy into going and collecting the data and we're going to use it for this year's analysis, but by taking a little bit more time to record the metadata, all this related material and documenting it in the same spreadsheet, you're giving that data legs to live in the future and be used in the future after you've moved on to a different position.
Exactly. So we have a question here from Jen McQuarrie. Jen asks, I was wondering if you could elaborate on using geometric mean for analyzing for E. coli. I was writing notes and didn't catch it.
So it's a geometric mean. it's a function in Excel, so you don't really need to get into the detail of how to calculate it. But it's useful for taking data sets where you have a big spread in your data from very small numbers to large numbers. It dampens the effect of the small and the large numbers and gives you a more representative mean, in this case geometric mean, a center point in that data. And so it tends to be the preferred method when dealing with bacterials, especially E. coli numbers.
Excellent. Thank you, Andy. Well, that seems to be the end of our questions for today. So again, Andy, thank you. A wonderful presentation. And as he mentioned, it will be available on the Atlantic Salmon Conservation Foundation website for folks who'd like to view it or use it as a resource in the future. Oh, and I just had a new question come in. So Jen does say thank you very much for your response there on geometric mean. We do have a new one from Esther Hales. Esther asks, is DO best taken on site, or can you still get an accurate reading several hours later using a hash field kit, and does refrigeration of the water sample help?
Ideally, DO should be determined on site. You will get changes even with refrigeration over time, and so it's take your kit to the river is my best advice.
Okay. Thank you. Okay, so maybe just a reminder to folks that we do have another presentation coming up in our series. Elsa Gorig at INRS will be speaking about culverts and the role that motivation and swim performance has on successful passage by salmonids. This presentation, though, is going to be in French. The question and answer session will be bilingual, however. The next English presentation in our series will be on February 17th. Raphael van der Stichel of the University of Prince Edward Island will be giving an introduction to QGIS, which is a free and open source geographic information system. So for those of you who are interested in learning more about it, this will be a great webinar. So registration and a list of webinars as well as past recordings is available on our website. And we'd like to thank you again for participating today. A huge thank you to Andy. And we hope you'll all be joining us again very soon. Thank you.